Hello, I am Delphine Lobelle, and I'm a postdoc at Utrecht University working on the global sinking characteristics of modeled biofouled microplastic, along with my co-authors listed here. The main question my work aims to answer is, how long does it take for biofouled microplastic to sink? So imagine we have a virtual ocean with algae drifting around, and a microplastic particle is placed at the surface. If we include 3D advection, this virtual particle moves and collides with the algae, which attaches, grows, and forms a biofilm. Once the density of the particle plus this biofilm is larger than its surrounding seawater, the particle sinks, and we define this as the sinking timescale. So how are the simulations set up? Well, the Nemo Medusa 2.0 ocean general circulation model is used for the hydrodynamic profiles and the biological data, such as the phytoplankton, which is converted to the algal concentration. The output data are on a 1/12 degree horizontal resolution and available as 5-day averages. The Ocean Parcels Lagrangian simulation framework is used to run 90-day simulations where particles are released once on a 2x2 degree global grid and at a 0.6 meter depth. 5 different particle sizes are used, from 1 millimeter to 0.1 micrometers, and 3 initially buoyant densities corresponding to different types of plastic are used. The densities have a very low impact on the qualitative results in this study, so I will only show the low density polyethylene results today, the 920 kilograms per meters cubed. And how do we determine when the particle sinks? So the equations behind the simulations are based on the Coy et al. 2017 model, where the attached algal growth is dependent on 4 different terms: the collision of ambient algae with the particle, plus the growth of the algae, minus the death and the respiration. Since the attached algae increases the density of the particle, this affects the sinking velocity, which is dependent on the density difference between the seawater and the particle plus biofilm, as well as the initial buoyancy of the particle, which is characterized by the initial size and density of the particle. When the sinking velocity and the surrounding seawater's vertical advection are downwards, the particle sinks. We can now determine the sinking timescale on a global scale for the biofouled microplastic. Here you see the 5 different sizes used in the study, from the largest, 1 millimeter, to the smallest, 0.1 micrometers, each time decreasing an order of magnitude. The sinking timescale goes from yellow to black, with yellow being the shortest and black being beyond 90 days. The first, most obvious feature is that the smallest virtual particles sink almost immediately throughout the globe, whereas the 3 largest sizes have these large black patches that coincide with the 5 subtropical convergence zones, or the gyres. These are known to be oligotrophic zones where very little algae are present. So we were curious to see whether particles released in these locations would sink if we extended the simulation time. So let's choose the location that is known to have one of the largest concentrations of ocean plastic on the globe, the North Pacific subtropical gyre. 25 particles of the largest size in our study, 1 millimeter, are released on a 2x2 grid within the black area, which is where the particles didn't sink within the 90 days in the previous plots. And this time the simulations are run for 1,000 days. As you see by the yellow colors, the particle trajectories largely remain within the convergence zone, and throughout this almost 3-year simulation time, all the trajectories remain at the surface, and only 2 of the particles actually manage to sink. And that's only within the first 100 days. So it seems that the 1 millimeter virtual microplastic largely floats in the North Pacific subtropical gyre. Now, how does seasonality play a role? Well, by looking at the surface algal concentrations averaged over March, April, May, we see that the high concentrations in the North Atlantic due to the algal spring bloom lead to earlier sinking of the virtual particles. The same goes for the spring in the southern hemisphere during September, October, November, where higher algal concentrations are seen in the Southern Ocean and hence shorter sinking timescales. To conclude, the sinking timescale of simulated microplastic that has undergone biofouling is affected by the algal concentrations and the initial size of the microplastic, more than by the initial density. Furthermore, the oligotrophic subtropical gyres accumulate virtual particles between the size of 1 millimeter to 10 micrometers, both due to the physical effects of convergence and the biological effects of lower algal concentrations. With that, I would like to thank you for listening, and please follow our Twitter page at YouFollowTheOcean to keep up to date with all of the Parcels team's progress. Thank you.